So continuing our study of ideals in these rings of integers, and as I said, we're going to talk about, last time we talked about unique factorization and how this failed, and I said I was going to fix this using ideals. So let me start giving you some basic facts about these ideals in these rings of integers. But before that, let me just remind you of a definition, is that of Noetherian. Because what we're going to do is, what we're going to prove is going to be not true just for rings of integers, but for more general rings, and we're just going to study these more general rings, because, well, we might as well. So here's definition 3.2.1. This is a reminder. You would have seen this. So let R be a commutative ring. Then R is called Noetherian. If any of the following equivalent conditions hold. So, what are they? One is that every ideal is finitely generated. Two is that every increasing chain of ideals, say I1 contained in I2, so on, is eventually constant. And three, which is maybe like a more abstract one, or it's the one, maybe sometimes uses Zorn's lemma. Every non-empty set S of ideals contains, this is the one that we use the most, contains a not necessarily unique unique maximal element or maximal member. Great. So these are there's some definition you've probably seen in algebra 3 or whatever algebra it is. If not, then yeah, this is the definition. The first one is maybe the first easiest one to understand. Every ideal is finitely generated, so every ideal can be written as everything looks like x1. All the ideals look like x1 to xn, where this is some set of elements in your ring. And then, but it turns out that the one that's most useful usually is the third one. So as an exercise, you can go and check that these three things are equivalent. So why am I talking about Noetherian rings? Well, here's a proposition. 3.2.3. If we have a number field, K be a number field, and OK, the ring of integers, then OK is a Noetherian ring. Well, great. So we know it's a ring. We just need to check that it's a Noetherian ring. So proof. Oh, one thing that we saw already, we saw in corollary 2.2.8 that OK is finitely generated as an additive group. Great, so we know the whole ring is finitely generated as an additive group. Now, any ideal, let's see, frac A inside of OK is an additive subgroup of here's a keyword, abelian group. Okay, so we know that OK is a ring. We know additively it's an abelian group. And we also know that OK is finally generated as an additive group. So if you have an ideal contained in an abelian finally generated group, then your ideal has to be finally generated. Therefore, A is also finitely generated. So OK is Noetherian. Now, let me highlight again the word abelian. Oh, yes, wrong black color to use. Does that? Oh. What color should I use? Green. Abelian is the key word here. If you had a additive subgroup of a random finitely generated group, it need not be finitely generated. This is weird, but it's true that you can find subrings of like polynomial rings which are not finitely generated. Of some, not polynomial rings, but some non-commutative rings. If you're non-commutative, then the thing doesn't work. But here, the key word is that OK is an abelian group. Cool. So these rings of integers are Noetherian, which is good. And here's something useful that we can say about the ideals, and so we'll come back to the Noetherianness later on. But here's something useful about that we can say already about the ideals in these rings of integers. So we have a number field, and A and OK an ideal. Then A contains some positive integer. And moreover, the quotient OK mod A is finite. So every ideal in some ring of integers contains some positive integer in it. So even if I give you an ideal which is generated by the number root 2, then that ideal generated by number root 2 in some field will contain some integer at some point. So let's prove this. And from that, it'll follow that this quotient is finite. And this quotient being finite is really key for us. So I'm going to just pick some element alpha in your ideal, different from 0. Let's assume that, I should say, A is a non-zero ideal. So I can find some element in my ideal that's not 0. And I'm going to let n just be its norm. The norm from K to Q of alpha. Then I claim that this n isn't contained in this ideal. So since alpha is different from 0, the norm is different from 0. Now, by proposition, one of the propositions that told us how to compute the norm, was proposition 1.7.6, we see that this norm can be written as alpha times some element beta, where beta is the product of all the conjugate roots. Yeah. So it's a bunch of algebraic integers. So it's contained in the ring of all algebraic integers, which we were calling Z bar. Moreover, beta is in OK, since beta equals n over. Beta is this, which is in. Since beta is n over alpha, which is, we know that's an element of K, but recall OK is the same thing as you take K and intersect it with Z hat. So I've said this element beta is an element of Z hat, it's a product of algebraic integers, but it's also, I can also write beta as n over alpha, which is an element of K, so it's contained in K and in Z hat, and this, if you go back to one of the remarks I made, this is exactly what OK should be. So since we start with an ideal, n equals alpha times beta is an OK, right? Alpha is an element of my ideal. I can multiply it by beta, which is some other element in OK, and that always has to be in the ideal, so this has to be, ooh, it's not OK, this should be, this should be A. Cool. Okay, so every ideal can pick an element, take its norm, and the norm of that element, which is an integer, has to be contained in that ideal. So I've shown that every ideal contains an integer, or some positive integer. I guess technically I have to worry about the signs, but you can arrange it so that the signs are positive. I think I said positive integer. Yeah. Let me say Willog. We can make n positive. Just by multiply by some sign, that'll work. So let's prove that the quotient is finite. So let's do this. First note that since A is some n, this element that I construct above is some element of A, then the ideal it generates, I'll turn it like this, is contained in the ideal A. It's usual ideal stuff. Therefore, if you think of the quotients, the size of this quotient of OK mod A has to be smaller than the size of OK mod this ideal N. This is just some basic group theory. Secondly, since OK is finitely generated, as an abelian group, as an additive, if you pick an integral basis, which we know exists, we already saw this a couple of lectures ago. If we pick an integral basis, we get an isomorphism as additive abelian groups. So you get OK is isomorphic to some bunch of copies of Z, Zn, where n is the degree of your field. This is what it means when I say OK is finitely generated as an additive abelian group. It means that there is some isomorphism to Z to the n. If you think of it, usually, if you had a basis like 1 alpha to the n minus 1, this was your basis, then any element in here can be written as A plus B alpha plus C alpha squared plus, I should use A0 plus A1 alpha plus A n alpha n minus 1. And what do you map this to? Well, you map this just to the vector A0, A1, A n minus 1. To just the row. You just map it to the coefficients. So this is, once you pick a basis, then say your basis, e.g. If your basis was like this, if you had a power basis, then every element can be written in terms of power basis, and then the coefficients are what give you this isomorphism. Anyway, that's a detour. All we care about is that OK looks like some z to the n. What does this mean? Therefore, OK mod the ideal generated by n is isomorphic to a bunch of copies of z mod nz, like this, which is finite. And therefore, I just said that the size of a mod of OK mod your ideal is smaller than the size of a mod of OK mod n. So using this, and I know that this thing is now finite. So my original quotient was finite. So OK mod a is finite. Great. So we can already say that we already know that all of these ideals in rings of integers, they always contain an integer and their quotient is always finite. So what I'm doing here in this section at the moment, I mean, I should make it clear, is that I'm giving some general definition, like Noetherian, and some properties of these rings of integers, because what I'm going to show in the next section is that these rings of integers form what's called a Dedekind domain. So I'm just setting up these facts, and so this section at the moment about the ideals and the ring is just to move on to the next section. So here I'm going to remind you of a lemma, which I'm sure you've seen. If not, the proof is in the notes, but I'm not going to go through the proof right now. So it just says that a finite integral domain. A finite integral domain is a field. So if you have any integral domain which is finite has to be a field. Obviously, an integral domain on itself doesn't have to be a field. But, the proof, you can just see the notes. Proof. See the notes. The proof isn't there. But this is some basic algebra. I expect that you may have seen this before in one of the algebra courses. If not, then go read the proof. Or just try and prove it yourself. It's not hard. So here's a corollary of all of this, which is that corollary 3.2.6. If I have a number field, then every non-zero, I guess I don't need to say non-zero. Usually when I say prime ideal, it's going to be, it always means non-zero, but non-zero prime ideal in OK is maximal. Great. So proof. It was by the things that we did just at the start when we were talking about ideals, and just recapping ring theory. So by proposition 1.22, we know P in OK is a prime ideal if and only if OK mod P is an integral domain. Now, by the previous result, by proposition, or two results above, by proposition 3.2.4, we know OK mod P is finite. So the previous lemma says if I take a prime ideal, then I know the quotient is finite, and because it's a prime ideal, I know the quotient is an integral domain. So this lemma tells me that it has to be the quotient has to be a field. So we know this is finite. So therefore by lemma 3.2.5, it's a field. So it's some finite field, and we know what all these finite fields look like. So now, again, by the results from the first chapter, by what's the same proposition, 1.1.22, P is maximal. because again, an ideal was maximal if and only if when you quotient out by it you get a field. So here is the key thing is that our quotients are always finite, and if you start with a prime ideal, then you get into a domain, and therefore you get maximal ideal. So this set of this general class of rings, which I'm going to talk about, which is called Dedekind domains, they're going to satisfy three things. One of them is that they're going to be Noetherian. That's why I talk about Noetherian. And the next one is going to be that every prime ideal is maximal. So we looked at this. And the next condition is going to be about something called integral closure. So let me just give you this definition. Definition 3.2.7. So I'm going to let R and A be rings with A contained in R, a subring. And X some element of R. Then we say X is integral over A. Right? If there exists, say, AI in A such that we have the following relation, x to the n plus a. So the n doesn't, there is some n such that you can get like this. So you can get such a relation. So what am I saying is that I have some element x in my bigger ring such that it satisfies some relation like this. So somehow it satisfies some polynomial. Think about satisfying some polynomial with coefficients in your subring. Say for some n. For some n. I'm going to let A primed be the set of elements of R which are integral over A. Then as we proved before that the ring of integers of a number field was a ring, you can somehow generalize this or modify it slightly, so we need to check that this A prime is again a ring. So similar to corollary 2.1.16, we can check how we can prove that A primed is a ring called the integral closure of A in R. And more generally, let's continue with this definition. In general, if R is an integral domain, maybe not more general, so maybe it's a moreover. If R is an integral domain, and we let frac R as usually is going to denote the fraction field of R, so it's a set of all elements A over B, such that A, B is in R, B is different from 0, so it's just the smallest field which contains the element R, the elements of R, be the field of fractions. Then we say R is integrally closed if it's integrally closed in its field of fraction. So you can do this generally if you have two rings R and A and one is contained in the other, then you can say about the integral closure of A in R, and this is what we were calling this A primed. But if I don't specify what integral closure in what, then it's assumed that I'm talking about the fraction field. Okay, great. So having integrally closed rings such that every prime ideal is maximal and that it's such that they're Noetherian, these three conditions are going to define to us Dedekind rings, which is what we're going to look at next. And that's where we're going to, the results for rings of integers are going to hold for, the results for Dedekind domains will hold for rings of integers. And so we're just going to study them and study the ideals there. But I'll finish here for now.